Okay. So today we're going to still talk about probability. This whole chapter about probability, and try to get into uh, more more than just basic probability. We're talking about multiple events happening today. So we're going to talk about the addition and the multiplication rule and when to use each of those uh, for finding the probability of some things happening. So fun times with addition and multiplication rule. So uh, we're going to talk about using the addition rule when we're trying to find an or probability. So finding the probability of an event A or event B occurring is the addition rule. So with that, you could have the occurrence that both of the events happen. That is important to know. And then, so the word or tells you addition. Or tells you addition rules. Or tells you to use which rule? Addition rule. Okay, so if you see or, you gotta know it's addition rule. Okay. The multiplication rule is used for and. Okay, event A and event B. So that is a probability of event A occurring and event B occurring. So if you see and, then you know it's the multiplication rule. If you see and, you know it's the multiplication rule. If you see and, you know it's which rule? Multiplication. Good. Yeah, I've learned to play the game. Good job. All right. So a compound event. What's a compound event? It's an event combining two or more simple events. So all of section 1 was about simple events, single things, individual things happening. A compound event is combining two or more of those simple events and knowing how we're combining them. So in English class, you had compound sentences, right? And compound sentences are joined by what words? And, or, and but. There are no buts in stats except for many. Okay, so stats and or is the only ones we do. We don't have buts, but we'll talk about some givens that are kind of like buts. So when we're talking about the addition rule, again we're looking for that compound word or in uh, our sentence or the questioning is we're looking for the word or somewhere there. Sometimes they'll write it out and give you that probability statement, probability of event A or event B, or like probability of me flipping a coin and rolling a die. That could be two events, right? And what's the probability of me rolling a 6 or landing on heads? If I do those two things at the same time, that would be a compound event, right? So flipping the coin and rolling a dice, that's a compound event if you're doing those two different things there at the same time. Two simple events combined together. So the or is the addition rule. And we add in such a way that every outcome is counted only once. Okay, so each outcome is counted only once in the probability. Okay. Probability of A or B is equal to the sum divided by the total number of outcomes in the sample space. We'll see some examples of this, but we want to be careful with the or that we are taking care of counting each outcome only one time. That kind of implies what? That there could be some overlap. That you could end up with some of the cases where you have the probability of the first event plus the probability of the second event, like they were two separate simple events. But then you could have the probability of both events happening. We've got to take that out. That's the overlap. That's the getting rid of counting twice. From a deck of cards, if I were ask you to draw, or before I get into that, a normal deck of cards, what does it contain? How many suits? 4. Okay, and if you didn't grow up playing cards, you may not know this, so we probably need to talk about a deck of cards. Let's talk about a deck of cards real quick, because we'll use that. I'll use that as an example a lot of times because it really is easy to calculate because the numbers are not big, and it gives us a lot of examples. So in a deck of cards, you have 4 suits. You have what are those 4 suits? Spades, clubs, hearts, and diamonds. Okay, so that's the 4 suits. In each suit, you have how many cards? How many cards are in a deck? 52. There are 4 suits. That would be 13. 13 cards in each suit. All right. In those 13 cards, what are the cards? You have an ace, a 2, 3, 4, 5, 6, 7, 8, 9, 10, a jack, a queen, and a king in every suit. Okay. So if you don't have a deck of cards, it might be good to have a deck of cards. So the dollar store has those. I've got a few decks in here. I don't have enough for every person, but so a deck of cards. That's what a deck of cards is made of. Jokers are not part of a normal deck of cards. The instruction card is not part of the normal deck of cards. Okay, so a normal deck of cards. This is what we're talking about. Okay, all right. So here is an example of using that deck of cards to talk about an OR problem that has some overlap. So if I ask you to drawing out of a deck of cards, what's the probability of drawing a 3 or a heart? Right? So probability of drawing a 3. So how many 3s are there? There's 4 of them. So probability of a 3 or a heart. All right? So that's what we're working on here. So probability of a 3 plus probability of a heart minus the probability of what?
The heart and the 3.
The heart and the 3. So what the probability of a 3 is 4 out of 52. The probability of a heart is what? 13 out of 52, right? Because there's 13 hearts. Or that reduces to 1/4. I'm going to do 13 out of 52. And then we're going to subtract away how many 3s and hearts. There's only one 3 of hearts card. And that's the overlap. So we got to take out that one that was the 3 of hearts. That's our overlap. That is, it's a 3 and it's a heart. So that's why we got to take that out. So we would then do that. 4 plus 52 plus 13 over 52 minus 1 over 52. That'd be 16 over 52. And that reduces to 4 over 13. All right. You guys have calculators on your desks. Check. That's 17 minus 1 is 16. I know that part's right. 4 goes into 16 4 times, and into 52
That's
13 times. So the probability of a 3 or a heart is 4 out of 13. That is an example of us having some overlap. This is counting how many 3s there were. This is counting how many hearts there were. This is counting how many were both of those. That's what you're taking out. things that are both of those. A disjoint event, disjoint, so if you disjoint your shoulder, what does that mean? It separates, right? So event A and event B are disjoint. That's also called mutually exclusive. Much harder to say, especially early in the morning. Mutually exclusive and disjoint mean the same things. If events are mutually exclusive, that means they cannot occur at the same time. An example of that from the deck of cards would be probability of drawing a heart or a diamond. That's disjoint because a heart cannot be a diamond, right? There's no way that happens. So there's no overlap if it's disjoint. No overlap if it's disjoint. So mutually exclusive or disjoint mean the same things, are events that don't have any overlap. Events that don't have any overlap. That's what a disjoint event is. Okay. So if it's disjoint, then with our little formula here, the minus p probability of A and B is subtracting what? 0, because it doesn't occur if it's disjoint. So if it's disjoint, you don't even have to find the overlap. Okay? Disjoint events don't have any overlap. Here's an example. Event A is randomly selecting someone for a clinical trial who is male. Event B is randomly selecting someone for a clinical trial who is female. The selected person cannot be both. Right? It's disjoint. Disjoint because they cannot be both. Events that are not disjoint. Randomly selecting someone taking a stats class. Randomly selecting someone who is female. Those are not disjoint, right? If I randomly selected someone in the school, there are several females in this room. Very, very good young ladies that are taking this stats class. But that is not a disjoint event. They are not disjoint. Okay? All right, so probability of A or B, the word or tells us addition rule. We need to know if it's a disjoint event or not. So that we need, if it is not disjoint, then we have to find the overlap. That's what we're finding out here. That's what we have to look for. Is if it says or, I need to know is there any overlap. So I need to know, is it a mutually exclusive event or not? Okay. So we don't double count. All right. Complementary events and the addition rule. So complement, remember, means the things that are not in that probability. If you had the probability of event A and its or its complement, so probability of A or complement of A, when you add those things together, it better equal 1. Okay, so probability of an event and probability of its complement, if you add those two things together, it should equal 1. Because if you're event A, if you're in this case, let's say if you're a heart, the probability of not being a heart should add up to the rest of the 52 card deck, right? Probability of a heart is 13 out of 52. Probability of not a heart would be 52 minus 13. 39. 39 plus 13 is 52. They should add up to be 52 out of 52. So event and its complement, if it's or between them and you add them together, you better get 1 or something ain't right. Now, what that allows us to do then is manipulate that little formula so that we can find the probability of the complement pretty quickly by just subtracting the probability of the event. when you're dealing with a deck of cards, that's only 52 things. But when you're dealing with a much larger set, maybe we don't want to try to count it. That counting out 39 cards isn't too bad, but counting out 7,642 things might be pretty bad, hard to do. So taking this little formula and doing the 1 minus is going to help us for complementary events. Okay? If we know the probability of an event, then we can find the complement, the probability of the complement of that event by just subtracting from 1. That's what this tells us here. Okay? Now, here's an example. Based on the journal article, the probability of randomly selecting someone who has sleepwalked is 0.292. So probability of sleepwalk is 0.292 based on this data from this neurology report. If a person is randomly selected, find the probability of getting someone who is not sleepwalked. 1 minus 0.292. You don't have to go and find that data and look up this study and count it up. You just say 1 minus 0.292 and you get the complement of that. The probability of that complement. All right, 1 minus the probability of sleepwalking. Does anybody sleepwalking here? Let's find that the most intriguing thing. I have a friend whose daughter does it, and it's like we'll just find her around the house. They have locks on the doors up top that she can't reach while she's walking around. So it was a bigger deal when she was younger. Now they don't have to worry about it so much. She's kind of doesn't do it as often now. She used to. So it's kind of interesting. I always find that just an intriguing thing. Nothing wrong with it. It's just some people do things that they just don't know that they're doing. So, all right, multiplication rule. So let's get into the multiplication rule. The key word for multiplication is what? And. Okay. Probability of event A and event B occurring. So it says in the first trial and event B in the second trial. And then we have this weird notation here. It says B and then it has this little straight up and down bar. A represents the probability of event B occurring after it is assumed that event A has already occurred. Okay, so there's times when that's important. Okay, it depends on if we're talking about the deck of cards. It depends on if you put the card back or not. If you drew out of the deck and you didn't put it back, that changes the probability of the second event. So that is an important thing. So probability of B given A has already happened. That's what this means. Probability of event B happening given that A has already happened. Okay? And with that, you get into this, the intuition that you have to have about the multiplication rule. So probability of event A occurring in one trial and event B occurring in the next trial, multiplying those probabilities together. But be sure that probability of event B is found by assuming that event A already occurred. So when you read the problem, they're going to say something about maybe with replacement or without replacement. Those are the key words. Because your probability of the second thing happening could be changed. So like, if you're talking about the deck of cards, if I ask you to draw 2 cards, well, are you drawing one card, looking at what it is, maybe writing it down, and then putting it back in the deck, shuffling them up, and then drawing the second card? Or are you pulling that card out saying, okay, I got that one, laying it down over here, and then going back to the deck? That changes the probability because the card deck doesn't have 52 cards in it anymore. But it changes the probability. Instead of out of 52, it would be out of 51. Or if we drew 5 cards at a time. We'll get into all that fun stuff later on. In the chapter, it gets a little bit more interesting what happens with that stuff. So be sure probability of event A is found, or event B is found after event A has already occurred. So you're looking for words about All right, so this is the formula here for the and. Probability of event A. It's the normal, regular, old, simple event probability like we did in section 1. There are 38 things. Probability of each thing is 1 out of 38. Probability of event B, given that A has already happened, that's going to depend on what the problem tells you about how the events are occurring. Are you putting the card back in the deck? If the problem on the quiz with the marbles, if I had 2 marbles I was going to draw, and I want to know probability of getting a blue one and a green one, the question is, did you put the blue one back after you drew it the first time? You have to know that in the problem, and they're going to tell you with replacement, without replacement, so that you know how to figure out the probability of B given A. Independent events. Independent events are when they do not affect one another. Event A does not affect the probability of event B. That would be in a case where there is with replacement. So if it's independent, event A does not affect event B's probability. They are not. They are independent of one another. What one does doesn't affect the other. Okay? If they are not independent, then they have to be dependent. So what happened in event A had some kind of effect on what the probability in event B was. Okay? So that is independent events, they do not affect one another. Dependent events, they do affect one another. That is not the same thing as joint and disjoint. Joint and disjoint have to do with overlap. Independent has to do with what does one event affect the probability of the other event. All right, so here's an example. 50 test results. There are 45 positive test results, 5 negative test results out of that, and for a total of 50. If 2 of these 50 subjects are randomly selected, notice in bold it says with replacement. Okay? Find the probability the first selected person had a positive test and the second one had a negative test. So we're finding probability of positive and probability of negative. So probability, we're finding the for A, we're finding probability of positive and negative. That's what we're finding. And it says with replacement. So that means that once we pick that first person, we're putting them back in the pool. That's what with replacement means. Okay? And so that would be independent events. You treat that as independent because it's with replacement out of that. And then B part says we're going to do that same problem, but without replacement. So with replacement, what's the probability of picking a positive? So probability of positive would be 45 out of 50. 45 out of 50. Probability of negative be 5 out of 50. Again, with replacement, we have 50 people in the bowl of names, right? So that'd be 5 out of 50. And we would multiply those two together, and that would give us our probability. So what is that? 45 times 5 divided by 50 squared. 0.09. Either 9 out of 100 or 0.09. Either of those would be sufficient. Without replacement, for B part, it looks the same for the positive one, because that's our first event. Probability of picking a positive one is 45 out of 50. But without replacement, that means once I picked that name out of the hat, I laid that little piece of paper over here on the side, and now I'm going back to the hat. So how many people are in the hat now? 49. We're assuming that when we picked the first one, we did get a positive one. So how many negative ones are there? There's still 5, but there are 49 to choose from now. So that creates a different probability. 45 times 5, still on top. 225 over 50 times 49, which is, I think that's going to, 9 out of 98, which as a decimal, 3 sig figs would be 0.0918. If you do that. So very, very close in probability here, but not the same. So with replacement, your bottom number stays the same all the time. Without replacement, your bottom number is going to go down by ever how many. Here is their work there. Without replacement, the second probability is that 5 out of 49, and then you get 3 sig figs there on that. Okay, so when you're sampling methods are critically important. That's why we spent a whole chapter talking about those things, all those sampling methods. If you're sampling with replacement, selections are independent events. If you're sampling without replacement, they're dependent events. Okay, so when you're sampling, you've got to make a decision about how you're going to do that. Are you going to sample with replacement or without replacement? That changes your probabilities of picking whatever type you're trying to sample out of that. So with replacement or without replacement. With replacement, they're independent. Without replacement, they're dependent upon one another. Know that those go together. All right, so here's that 5% coming up again. We talked about that a little bit earlier today. But this is treating dependent events and independent events. There's a 5% guide to cumbersome calculations. What's cumbersome? That's a fun word. That's the dude who played the Grinch, right? And Doctor Strange. Benedict Cumbersome. Yeah, that's 5%. When sampling with replacement, without replacement, the sample size, if it is no more than 5% of the size of the population, we're going to treat that as independent, even though they're actually dependent, because the sample size is so small. And if you think about if I'm picking from the population of the whole country, I don't want to do the math if I pick, I'm looking for, my son's on the spectrum, so if I'm trying to pick 10-year-old boys that are on the autism spectrum in the whole country of the United States. And that's what I'm looking for. My one kid out of, how many 10-year-olds are there in the United States? Millions, right? It's a really large number, right? So with that one, the 5% guide here is telling us if your sample size ends up being less than 5% out of the whole population, you're going to treat that as independent anyway. You're not going to reduce the bottom number. Okay? If the sample size is less than 5% or no more than 5%. So no more than would be 5% or less. If it's 6%, we're gonna do the reduce the bottom number thing. If it's 6%. But if it's 5% or less, then we're going to treat it as independent. 5% or less, we'll treat it as independent. Because there's going to be very little difference in the probabilities. Okay. So here's a drug screening question for the 5% thing to kind of give us an idea why we would even do that. So, assuming that 3 adults are randomly selected without replacement from the 247,436,830 adults in the United States. That number is different now. This data is more than a day old, so it's different. So assume that 10% of the adults of the United States use drugs. Find the probability that 3 selected individuals all use drugs. Okay? So when we're looking at this, assume that 10% of the adults, so the probability of what we're doing here is the probability of an adult doing drugs is 1 out of 10, right? So we're selecting from this huge number, right? This huge population, we're selecting from there. But because the 3 adults are selected without replacements, these 3 events should be dependent. But we can treat them as being independent by applying that 5% guideline. Because if we're picking 3 people, what percentage of 247 million is that? Calculate it for me. Tell me what it is. What percent of 247 million 436,830? What do we get? The decimal. How many zeros after the decimal? 7 zeros after the decimal. And so it's 7 zeros and then a 1. That's what percent of the population we're picking. That is way under 5%, right? So in this case, the probabilities are going to be so minuscule difference between treating as dependent events versus independent events that it isn't worth the calculation to do 247,336 or 436,830 for the first probability, and then do 247,436,829 for the second probability, and then the next one would be 828 on the end of that. It wouldn't make sense to do that. We're going to use that 10% probability that the problem told us about. 10% times 10% times 10%. Multiply that together, and you get 0.001, and 3 sig figs would be 00 out of that for the probability of that. Much easier calculation than doing, what is 10% of 247,436,830? Getting that number and then going down from there. That would be very cumbersome calculation. This you could do quickly, and it's going to be just as rounded wise, probably going to be not one bit of difference in the number like that, because the sample is so small. So 5%, cumbersome calculation rule. All right, redundancy, important. When we're dealing with the multiplication rule with redundancy. Redundancy is used to increase the reliability of the system. Our eyes have passive redundancy in the sense that if one of them fails, we will still be able to see. Right? So when you're designing something as an engineer or building a system, you want redundancy in that system so that if one thing fails, it doesn't cause the whole thing to crash. Right? The redundancy out of that idea. So finding when we're dealing with redundancy in the multiplication rule, here's an example. I think it's easier to understand here. So modern aircraft are now highly reliable. One design feature is the use of redundancy. That if the altimeter doesn't tell you how high you are in the air, it doesn't cause everything else to just not work. Right? Critical components are duplicated, so that if one fails, the others will continue to work. Such as each engine has a separate fuel line running to it. If you're on a jet that has 2 engines on each wing, that each engine has a separate fuel line, so that if the fuel line to the first engine fails, you're still getting fuel to the second engine. Where in the past, they may have ran one fuel line that split off at each engine. The redundancy is running extra things there. So, for example, the Airbus twin engine has 3 independent hydraulic systems, so that if one system fails, full flight control is maintained with another functioning system out of that. So the hydraulics are operated by pumps, and hydraulics pump liquids through pistons and hoses to make the landing gear go down. And sometimes you only, like on a tractor, older tractors, you have one hydraulic pump, and it ran the lift in the back of the tractor and the lift in the front of the tractor. If that hydraulic pump failed, you couldn't pick things up from the front, you couldn't pick things up from the back at all. What they're saying is, for us, we have 3 independent hydraulic systems. So if the hydraulic system, we have a landing gear hydraulic system, we have a controls hydraulic system, and then we have the hydraulic system that operates the flaps and rotors. 3 separate ones instead of one pump. That's the redundancy in that. So on a typical flight, the probability of a hydraulic system failure is 0.002. If Airbus 310 were to have one hydraulic system, what's the probability the aircraft's flight control would work for a flight? So if it only has the one hydraulic system, not 3, what's the probability that the flight control would work? So we have a probability of failure. So the probability of it not failing would be working, right? So that's the complement of failure. So 1 minus the 0.002. So the probability of it working is 0.998, which is pretty good, right? That's good. That's really good. Okay. Part B says, given that it actually has 3 independent hydraulic systems, what's the probability on a typical flight control can be maintained with a working hydraulic system? Okay. So B part, we're taking 3 independent events here. We have probability of failure for the first hydraulic system, it's 0.002. The second hydraulic system has the same probability of failure. Third one has the same probability of failure. We multiply all 3 of those together, and that's the probability of all 3 of them failing. That's pretty small, right? Then, so the probability of all 3 of them failing is that. So the probability of at least one of them working is 1 minus that. Is this better or worse than the 0.998? It's a lot better, really. It's almost certain that it will work, right? But that's the idea of that redundancy out of that. So here we're taking that probability and we're figuring out, okay, what's the probability of at least one of those out of there? So some extra information here. So using that, we the failure decreased from a factor of 1/3, or not by a factor of 1/3, but by a factor of 1/250,000, which is way big difference in there. So 3 hydraulic systems definitely decreases our chances of failure, which if you're flying in a plane, you don't want that to happen, right? I wouldn't. I'd be in panic mode out of that. So summary of our addition and multiplication rule. So addition rule, what word are we looking for? What do we have to take care of with the OR problems? Overlap. Make sure you're not counting everything twice. That's where that overlap comes in. So make sure you're only counting each outcome one time. So that overlap is a big deal. The multiplication rule, we need to decide if the events are independent or dependent. Need to decide that before we start working the problem. Okay. And then take into account if they're dependent, your second probability is gonna change. That's what you need to remember about multiplication rule. And the key word for multiplication rule is and. Okay, so or for addition, and for multiplication. So this is getting, and this gets more fun because you can do a lot more stuff once you get into this. On page 155 is where we'll be. 1 through 34 would be good. Get you some of the challenges and stuff at the end there. 4-2. So lots of stuff in there. The key is being able to read a problem and know what you should do. That's the one thing that you need to really focus on is being able to read a problem and know what you should do and how you should work it. Is it addition rule, multiplication rule? Is there overlap? Is there not overlap? Is there a independent or dependent events?